Those stars you see at night, they might as well be painted on a dome above us because the distance, the energy, the physics, everything about the universe conspires to make interstellar travel not just difficult, but functionally impossible. Today, I will show you exactly why we're trapped. And here is a question for you. What's the first question you'd ask an alien civilization if we made contact with them tomorrow? Let me know in the comments below. I will pin the most creative answer. Now let's begin. Picture this. You're standing on Earth, looking up at the night sky. You spot Alpha Centauri, our nearest stellar neighbor. Looks so close, doesn't it? Just a bright point of light twinkling in the darkness. But here's what that innocent sparkle is hiding from you. Alpha Centauri is 25 trillion miles away. That's not a typo, 25 trillion miles. To put that in perspective, if you could somehow drive a car at highway speeds toward Alpha Centauri, it would take you more than 43 million years to get there. The entire history of our species, from the first humans walking upright to you watching this video right now, spans only about 300,000 years. You'd need to live that entire history 143 times over just to make the drive. But of course, we wouldn't use cars. We have rockets, right? Surely our most advanced spacecraft can do better. Let's talk about the fastest human-made object ever created, the Parker Solar Probe. This magnificent piece of engineering reached speeds of over 430,000 miles per hour as it dove close to the Sun. That's mind-blowing, right? At that speed, you could travel from New York to Los Angeles in less than 7 seconds. You could circle the entire Earth in about 3.5 minutes. It's faster than anything humanity has ever built. And yet, if the Parker Solar Probe were headed toward Alpha Centauri at its maximum speed, it would still take over 6,000 years to arrive. Think about that. When it launched, the pyramids of Egypt hadn't even been built yet. The entire span of recorded human history would need to happen again, from beginning to end, just to complete a one-way trip to our closest neighbor. Now you might be thinking, okay, but technology improves, right? We'll build faster rockets. And that's where things get truly devastating, because the problem isn't just engineering, it's not just about building a better engine or finding the right fuel. The problem is physics itself. The universe has speed limits, and they're not suggestions. They're laws written into the fabric of reality, and breaking them isn't a matter of being clever or determined. It's impossible in the most fundamental sense of that word. Let's talk about the speed of light. In science fiction, breaking the light barrier is routine. Ships jump to warp speed, enter hyperspace, or punch through into some alternate dimension where the rules don't apply. It makes for great stories, but in our universe, the speed of light isn't just fast, it's the ultimate cosmic speed limit, and nothing with mass can ever reach it, let alone exceed it. Light travels at approximately 186,000 miles per second. That's fast enough to circle Earth more than 7 times in a single second. And even at that incredible speed, light from Alpha Centauri takes 4.3 years to reach us. That's why we call it 4.3 light years away. Now here's where it gets interesting, and by interesting, I mean absolutely terrifying for our dreams of star travel. As you accelerate an object closer and closer to the speed of light, something strange happens. The object gains mass, not because you're adding material to it, but because that's how physics works at relativistic speeds. The faster you go, the more massive you become, and the more massive you are, the more energy you need to accelerate further. It's a vicious cycle that creates an insurmountable wall. To actually reach the speed of light, you would need infinite energy, not a lot of energy, not more energy than we can currently produce. Infinite energy. As in, all the energy in the universe wouldn't be enough. The laws of physics don't just make light speed travel hard, they make it impossible. But let's be optimistic for a moment. Let's say we could somehow reach 10% of light speed. That would be revolutionary, an achievement beyond anything we've accomplished so far. At 10% light speed, you'd be traveling at about 18,600 miles per second. That's so fast that you could travel from Earth to the Moon in about 13 seconds. You'd cross the entire solar system in hours instead of years. It would represent a technological leap comparable to going from horse-drawn carriages to supersonic jets. And yet, even at that astonishing speed, it would still take 43 years to reach Alpha Centauri. 43 years of continuous travel through the void. No stops, no resupply, no turning back. Think about what that means for any crew making that journey. You would launch as a young adult and arrive as a senior citizen, assuming you survived the trip at all. Your entire career, your prime years, your life would be spent in a small spacecraft, hurtling through the darkness. And that's just to reach the nearest star system. Most potentially interesting star systems lie much, much farther away. The star systems we've identified with potentially habitable planets are dozens, hundreds, even thousands of light years distant. At 10% light speed, reaching them would take centuries or millennia. If you're enjoying this deep dive into the cosmos and want to support this growing channel, hit that subscribe button and give this video a thumbs up. It genuinely helps more people discover these mind-expanding cosmic truths, and I'm grateful for every single one of you joining me on this journey through space and time. But speed is only the first problem. Let's talk about what happens when you're actually traveling at these incredible velocities. Space isn't empty. We call it the vacuum of space, and compared to Earth's atmosphere, it basically is a vacuum. But basically empty and completely empty are very different things when you're moving at a significant fraction of light speed. Space contains dust, tiny particles, stray atoms of hydrogen and helium left over from the Big Bang. At normal speeds, these pose no threat whatsoever, but at relativistic speeds, every single particle becomes a potential bullet. Here's why. Kinetic energy depends on velocity. When something hits you at normal speeds, the impact is proportional to the square of that speed. But we're not talking about normal speeds, we're talking about tens of thousands of miles per second. At those velocities, even a grain of dust carries enormous destructive potential. Imagine a speck of matter smaller than the period at the end of this sentence hitting your spacecraft at 10% light speed. The energy released would be comparable to a bomb exploding. A single grain of sand at that speed would impact with the force of several tons of TNT. Your spacecraft wouldn't just be damaged, it would be obliterated, vaporized in an instant, leaving nothing but an expanding cloud of plasma where moments before there had been a vessel carrying the hopes and dreams of an entire civilization. And you can't dodge this problem. Space might seem empty, but averaged across interstellar distances, there's roughly one hydrogen atom per cubic centimeter. That doesn't sound like much, but when you're traveling through trillions upon trillions of cubic centimeters, you're going to hit a lot of atoms. Some estimates suggest that a spacecraft traveling at a significant fraction of light speed would encounter the equivalent of a nuclear explosion's worth of particle collisions every single second of the journey. You're not sailing through a calm cosmic ocean. You're flying through a minefield where every particle is a potential catastrophe waiting to happen. Scientists have proposed solutions, of course. Maybe we could put massive shields at the front of the spacecraft, thick enough to absorb the impacts. But here's the problem. Shields have mass. And remember what we discussed earlier about accelerating mass to high speeds? The more massive your spacecraft, the more energy you need to get it moving. It's a cruel equation. The protection you need to survive the journey makes the journey itself exponentially more difficult to achieve. Every ton of shielding you add means exponentially more fuel, which means more mass, which means more fuel, in an endless spiral of diminishing returns. Some researchers have suggested using magnetic fields to deflect charged particles before they hit the ship. It's an elegant idea. Instead of a physical shield that adds mass, you create an invisible protective bubble of magnetic force. The Breakthrough Starshot initiative, started in 2016 by entrepreneur Yuri Milner and backed by physicist Stephen Hawking before his passing, has been exploring ideas like this. But magnetic fields only work on charged particles. Neutral particles sail right through. And creating a magnetic field strong enough to deflect particles at relativistic speeds would require enormous amounts of energy, which brings us back to the same fundamental problem: energy. Let's talk about energy in more concrete terms, because this is where the devastation becomes truly apparent. To accelerate even a small spacecraft to 10% of light speed would require more energy than humanity currently produces in an entire year. We're not talking about the energy to power a city or even a country. We're talking about every power plant, every solar panel, every wind turbine, every nuclear reactor on Earth running at full capacity for 12 months, and all of that energy directed toward launching a single spacecraft. And that's just for a tiny probe, something weighing maybe a gram or two, about the mass of a paperclip. The Breakthrough Starshot project envisions exactly this kind of mission. Their plan involves ultralight spacecraft called light sails, thin reflective sheets attached to tiny electronic payloads weighing no more than a gram. These would be accelerated not by rockets, but by enormous laser arrays on Earth, beaming powerful light at the sails to push them forward through radiation pressure. According to their calculations published in recent research through Caltech and other institutions, in 2025, reaching 20% of light speed might be theoretically possible with this approach. At that velocity, a probe could reach Alpha Centauri in about 20 years. It sounds promising, doesn't it? Finally, a glimmer of hope. But let's look at what this actually requires. The laser array needed would have to be roughly 100 gigawatts, about the same power output as 100 large nuclear power plants, all focused into a single beam. This beam would need to remain precisely targeted on a sail just a few meters across as it accelerates away from Earth at increasing speeds. The engineering precision required makes building the pyramids look like child's play. And all of this monumental effort, all of this energy and expense, would send a spacecraft the size and weight of a butterfly to another star system, not a human, not even a robot capable of meaningful exploration, a tiny probe carrying perhaps a camera and a simple transmitter. And here's another crushing reality: that probe couldn't slow down when it arrived. At 20% light speed, it would scream past Alpha Centauri in a matter of hours, maybe capturing some images and data as it flew by, then continuing on into the depths of space forever. There's no fuel on board to decelerate, no way to stop. It's a one-shot flyby mission after 20 years of travel and the energy equivalent of a significant fraction of our civilization's total power output. You get one brief glimpse, a few precious moments of observation, and then it's gone forever into the cosmic night. Now imagine trying to send humans on a similar journey. Humans need life support. They need water, food, air, radiation shielding, living space, and redundant systems in case anything breaks. A human spacecraft capable of interstellar travel would need to be massive, potentially weighing thousands of tons. Accelerating that much mass to even a fraction of light speed would require energy on a scale that makes our current capabilities look primitive. We're talking about energy requirements that exceed anything our civilization could produce, even if we covered every square meter of Earth's surface with solar panels and built fusion reactors in every major city. Some scientists have proposed using antimatter as fuel. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass directly into energy according to Einstein's famous equation E equals mc squared. It's the most efficient energy conversion process possible in our universe. A single kilogram of antimatter colliding with a kilogram of matter would release energy equivalent to approximately 43 megatons of TNT, roughly the same as the largest nuclear bomb ever detonated. In theory, antimatter propulsion could achieve a significant fraction of light speed, but here's the devastating catch: we can barely produce antimatter at all. The largest particle accelerators on Earth, like CERN's Large Hadron Collider, can produce tiny amounts of antimatter, but we're talking about a few nanograms per year. That's billionths of a gram. At current production rates, it would take approximately 100 million years to produce a single gram of antimatter. And you'd need thousands of kilograms for an interstellar mission. Even if we improved our production capabilities by a factor of 1,000,000, which would represent a technological leap beyond anything we can currently imagine, it would still take 100 years to produce enough antimatter for one mission, and that's assuming we could store it safely, which is another monumental challenge, since antimatter annihilates instantly upon contact with normal matter. If you're fascinated by the challenges that keep us confined to our solar system, you might want to check out my other video exploring why no aliens have come to visit us. It dives deep into something called the Fermi paradox and examines whether the same barriers keeping us from traveling to the stars might also be keeping potential alien civilizations trapped in their own cosmic neighborhoods. It's a mind-bending exploration that connects perfectly to what we're discussing here. You'll find it linked in the description below and on the card above. Let's shift gears and talk about time, because even if we somehow solved all the energy problems, even if we found a way to accelerate a crewed spacecraft to a meaningful fraction of light speed, time itself becomes an enemy. Einstein's theory of relativity tells us that time doesn't flow at the same rate for everyone. The faster you move, the slower time passes for you relative to someone standing still. This is called time dilation, and it's not science fiction. It's measurable, proven physics. GPS satellites orbiting Earth have to account for time dilation, or they'd give you directions that were miles off target. At relativistic speeds approaching the speed of light, time dilation becomes extreme. From the perspective of someone on a spacecraft traveling at 90% light speed, time would pass much more slowly than for people back on Earth. A journey that takes 10 years for the travelers might see 50 years pass on Earth. The astronauts would return younger than their own children. But here's what makes this devastating rather than just interesting. Time dilation doesn't help you cover distance faster from Earth's perspective. If you're traveling to a star system 100 light-years away, at least 100 years will pass on Earth before any signal from you could possibly return. Your family, your friends, everyone you knew would be long dead before you could even send word that you'd arrived safely. This creates a profound psychological barrier. Would you volunteer for a mission knowing that everyone you love would die while you were gone? Knowing that the world you left behind would be transformed beyond recognition by the time you returned. If you returned at all? Some theorists suggest generation ships as a solution, massive vessels carrying entire communities that would live, reproduce, and die during the centuries-long journey, with only distant descendants eventually reaching the destination. But this introduces an entirely new category of problems. A generation ship would essentially be a small, closed ecosystem hurtling through space for hundreds or thousands of years. Everything would need to be recycled: water, air, nutrients, everything. There could be no margin for error, no possibility of resupply. Any failure of the life support systems would mean extinction for everyone aboard. The ship would need to be completely self-sufficient, capable of growing food, purifying water, manufacturing replacement parts, and maintaining complex machinery for longer than any human civilization has ever existed continuously. Think about that for a moment. The longest-lasting continuous civilizations in human history have persisted for perhaps 3,000 or 4,000 years before transforming into something unrecognizable. We're asking a small community aboard a generation ship to maintain perfect technological and social stability for potentially 10,000 years or more. Every cultural practice, every piece of technical knowledge, every system and procedure would need to be preserved flawlessly across hundreds of generations. One generation forgetting how to repair the water recycling system could doom everyone who comes after. And then there's the social dynamics. How do you maintain cohesion, purpose, and mental health in a small, closed community that will never see their destination? The original crew members who departed Earth did so voluntarily, with purpose and excitement. But what about their children, born into a metal cylinder in the void, who never chose this fate? What about their grandchildren and their great-great-great-grandchildren, each generation further removed from Earth and still impossibly distant from their destination? History shows us that isolated communities tend toward conflict, schism, and social breakdown over much shorter time periods. Asking humans to maintain a stable society in a sealed container for millennia might be asking for something psychologically impossible. Let's examine radiation, because this represents yet another layer of devastation in our dreams of reaching the stars. Here on Earth, we're protected by something so valuable that we rarely think about it: our planet's magnetic field and thick atmosphere. These natural shields protect us from a constant barrage of deadly radiation streaming through space. Cosmic rays, high-energy particles accelerated by supernovas and other violent cosmic events, zip through the galaxy at nearly light speed. Solar wind, a stream of charged particles from our Sun, constantly flows outward. Without Earth's protective bubble, these would sterilize our planet's surface in short order. Astronauts on the International Space Station, just 250 miles above Earth's surface, still receive significant protection from our magnetic field. Even so, they're exposed to radiation levels roughly 10 times higher than what we experience on the ground. For missions to the Moon or Mars, which venture beyond our magnetic protection, radiation becomes a serious concern. Astronauts on a journey to Mars would be exposed to radiation levels hundreds of times higher than on Earth, but at least those missions last months, not years. An interstellar journey would subject travelers to this bombardment for decades, centuries, or millennia. Cosmic radiation doesn't just increase your cancer risk, though it certainly does that. At the levels encountered in deep space over long periods, radiation damages DNA in ways that accumulate and compound. Your cell's repair mechanisms would be constantly working overtime, and eventually they'd fall behind. Beyond cancer, chronic radiation exposure causes cataracts, cardiovascular disease, nervous system damage, and accelerated aging. After just a few years in deep space without adequate shielding, an astronaut's biological age might be a decade or more ahead of their chronological age. Over the timescales required for interstellar travel, the radiation dose would be absolutely lethal without extraordinary protection. The obvious solution is shielding, but remember our earlier discussion about mass and energy. Effective radiation shielding is heavy. The best materials for blocking cosmic rays are dense elements or thick layers of lighter materials like water or polyethylene. To provide adequate protection for humans, you'd need shielding several meters thick, surrounding the entire habitable area of your spacecraft. That could easily add hundreds or thousands of tons to your ship's mass. And we've already established that accelerating mass to relativistic speeds requires prohibitive amounts of energy. Every ton of shielding you add makes the energy requirements that much more impossible to achieve. Some researchers have proposed using magnetic shielding similar to Earth's natural protection. You'd generate a powerful magnetic field around your spacecraft to deflect charged particles. It's theoretically possible, and it wouldn't add much mass compared to physical shielding, but it would require enormous amounts of continuous power for the entire journey. Where does that power come from? Solar panels become useless once you're far from a star. Nuclear reactors could work, but they have limited fuel supplies and would eventually run out on a journey lasting decades or centuries. And magnetic fields, remember, only protect against charged particles. Neutral particle radiation and gamma rays pass right through as if the field wasn't even there. There's another radiation concern that becomes critical at high speeds. Remember those hydrogen atoms scattered throughout space that we discussed earlier? At relativistic speeds, even these normally harmless particles become sources of radiation. When you collide with stationary atoms at a significant fraction of light speed, the impact creates what's called forward radiation. From your perspective aboard the spacecraft, it's as if you're flying into an increasingly intense beam of radiation that grows stronger the faster you go. At around 75% of light speed, this forward radiation becomes so intense that it would deliver lethal doses to any unshielded crew within seconds. The very act of traveling fast enough to make interstellar distances manageable creates a radiation environment so hostile that survival becomes nearly impossible. Now let's discuss navigation and communication, because even if you solved every problem we've discussed so far, you'd still face challenges that seem purpose-built to crush our interstellar ambitions. When you're traveling between stars, you can't just point your ship in a direction and hope for the best. Space is in constant motion. Stars orbit the galactic center. Planets orbit stars. Everything is moving relative to everything else. Alpha Centauri, our nearest neighbor, is moving relative to our solar system at about 12 miles per second. Over the years or decades your spacecraft is in transit, your target will have moved billions of miles from where it was when you launched. You'd need to constantly calculate trajectories, accounting for the motion of your departure point, your destination, and your spacecraft itself. And you'd need to make course corrections along the way, which requires fuel, which adds mass, which increases energy requirements. But here's what makes this truly devastating. The distances involved mean that even traveling at light speed, your navigation data is always outdated. If you're 3 light years from Earth, any information you receive about your trajectory is showing you where everything was 3 years ago. Any corrections you make take 3 years to be seen by mission control on Earth, and their response takes another 3 years to reach you. You're essentially navigating blind, relying on predictions and models rather than real-time data. Communication delays create their own special kind of isolation. Imagine being the crew of an interstellar vessel. You send a message back to Earth. We've encountered a critical problem with the reactor. That message, traveling at the speed of light, takes years to reach home. Engineers on Earth work on the problem and send back a solution. Years later, you receive their response. By then, you've either solved the problem yourselves or you're dead. Every decision, every crisis, every moment of doubt must be faced alone, knowing that help is always years away in both directions. The psychological weight of that isolation is difficult to overstate. And what about after generations have passed aboard a generation ship? The people born in transit have never seen Earth except in recordings. It's not their home, it's ancient history, something their great-great-great-grandparents left behind. Messages from Earth would be arriving from a world they don't know, offering advice and information that's decades or centuries out of date by the time it arrives. Would they even still care about maintaining contact? Would they still consider themselves human in the way we understand it? Or would the isolation and unique pressures of their environment create something fundamentally different? Here's another devastating reality about interstellar distances. You can't see where you're going. Even our most powerful telescopes can't resolve planets around other stars into anything more than indirect evidence, or, at best, tiny dots. We can detect exoplanets through various methods, watching for the slight dimming when they pass in front of their stars, or detecting the tiny gravitational wobble they create. We can make educated guesses about their size, mass, and distance from their star, but we can't see their surfaces. We can't know if they have atmospheres, oceans, continents, or life until we actually get there. Imagine committing to a journey that will take decades, centuries, or generations, investing resources that represent a significant fraction of your civilization's total wealth, sending brave explorers on a one-way trip into the void, all based on indirect evidence suggesting a planet might potentially be habitable. You won't know if you made the right choice until the journey is complete. And if you were wrong, if the planet turns out to be tidally locked with one side burning and the other frozen, if it has an atmosphere of sulfuric acid, if it's geologically dead or seismically hyperactive, or any of 1,000 other conditions that would make it unsuitable, there's no coming back, there's no second chance. You've spent generations traveling to a dead end and you're stranded light years from anywhere else. The economic devastation of interstellar travel deserves its own discussion. Let's try to wrap our minds around the costs. The International Space Station, humanity's most expensive single object ever built, cost roughly $150 billion over several decades. It orbits 250 miles above Earth. The Apollo program, which sent humans to the moon 250,000 miles away, cost about $280 billion in today's money. These represent some of the most ambitious projects our species has ever undertaken, and they barely left our cosmic doorstep. Now scale that up to interstellar distances. We're not talking about millions of miles or even billions. We're talking about trillions upon trillions of miles. The engineering challenges are exponentially greater. The energy requirements are exponentially greater. The timeline is exponentially longer. A conservative estimate for the cost of even an unmanned interstellar probe mission might be in the trillions of dollars. A crewed mission? Tens of trillions at minimum, possibly hundreds of trillions. That's not just more money than any single nation has. That's more money than exists in the global economy. The total GDP of Earth, every good and service produced by every human everywhere, is around $100 trillion per year. An interstellar mission could easily cost multiple years' worth of total global productivity. And for what return? There's no resource in another star system that would justify the cost. Gold, platinum, rare earth elements, whatever you might imagine finding, would cost exponentially more to retrieve than it could possibly be worth. You can't establish trade routes across light years. You can't exploit resources that are decades or centuries away. There's no economic incentive whatsoever. The only justification could be pure exploration, the advancement of knowledge, or survival if Earth becomes uninhabitable. But even survival doesn't make the economics work. It would be infinitely cheaper to build habitats in our own solar system, or to restore Earth's environment, or to construct underground cities, or virtually any other solution than attempting interstellar colonization. Let's talk about something that doesn't get discussed enough in conversations about interstellar travel: the sheer mechanical complexity and the certainty of failure. Every machine ever built by humans eventually breaks down. Your car needs maintenance. Your computer will eventually die. Even the most robust systems on Earth, built with the finest materials and maintained by experts, have finite lifespans. Now imagine a spacecraft that must function flawlessly not for years, but for decades, centuries, or millennia, with no possibility of external repair or replacement parts beyond what you brought with you. The Voyager spacecraft, launched in 1977, are the most distant human-made objects in existence. They've been traveling for nearly 50 years and have just barely entered interstellar space, the region beyond our sun's influence. These remarkable machines have lasted far longer than their designers expected, and yet they're already failing. Their power sources, radioactive thermoelectric generators, produce less electricity every year as their plutonium decays. Systems are being shut down one by one to conserve power. Scientists estimate both Voyagers will go completely silent sometime in the 2025 to 2030 range, just 50 to 53 years after launch. And these are simple probes with no life support, no complex machinery. Nothing but basic instruments and transmitters. A crude interstellar spacecraft would be orders of magnitude more complex. Life support systems with countless moving parts, filters that need replacing, pumps that can fail. Computer systems subject to radiation damage that accumulates over time, corrupting data and causing malfunctions. Hull integrity that must be maintained despite micrometeorite impacts and the stress of prolonged acceleration and deceleration. Every single component is a potential point of failure, and you have thousands upon thousands of components. The probability that something critical fails approaches 100% over the timescales involved. You might argue that the crew could repair problems as they arise. That's true for some issues, but it assumes you brought spare parts for everything that might break. How do you predict what will fail over a journey lasting centuries? How much mass do you dedicate to spare parts and raw materials? And what about manufacturing? Can you machine new parts aboard the ship if something breaks that you didn't anticipate? That requires bringing machine tools, raw materials, and crew members with the knowledge to use them. More mass, more complexity, more points of failure. There's a concept in reliability engineering called cascading failure. One system breaks, which puts stress on related systems, which causes them to fail, which damages other systems in a domino effect. In a spacecraft far from any hope of rescue, a single cascading failure could mean extinction for everyone aboard. Your water recycling system breaks. You try to fix it with backup components, but they're not quite right, and they fail too. Now you're running through your reserve water faster than anticipated. You try to reduce consumption, but that stresses the crew physiologically and psychologically. Stress leads to mistakes. Mistakes lead to more failures. Within weeks or months, a cascade that started with a broken pump has doomed the entire mission. And then there's the data storage problem. How do you preserve information for hundreds or thousands of years in a functional, accessible format? We've had digital storage for less than a century, and already early formats are unreadable. 8-inch floppy disks, punch cards, magnetic tape from the 1960s all require specialized equipment that barely exists anymore to read. The data might be physically intact, but it's effectively lost because we can't access it. Now imagine a generation ship where the original crew recorded critical technical information, but after 20 generations, the systems to read that information have broken down or been replaced. Future generations might be living aboard a ship whose inner workings they no longer understand, unable to repair problems because the knowledge has been lost. This brings us to the devastating reality of knowledge preservation across generations. It's not just about digital storage. It's about maintaining an entire technical civilization inside a closed container. Every specialty, every skill, every piece of knowledge needs to be passed down continuously. But how do you maintain specialization in a population that might only number a few hundred or a few thousand people? On Earth, we can support specialists because our population is in the billions. You can have experts who spend their entire lives studying obscure subfields because there are millions of other people doing all the other necessary work. On a generation ship, everyone needs to be a generalist to some degree. You can't afford to have someone who only knows how to repair one specific system, but generalists don't have the deep expertise that specialists possess. Over generations, as knowledge gets compressed and simplified for transmission to the next generation, details get lost. Crucial understanding erodes. After 20 or 30 generations, the people aboard the ship might only understand their systems at a surface level, capable of routine maintenance but unable to truly repair or innovate when something unexpected goes wrong. Human history provides countless examples of knowledge being lost. The Romans built aqueducts and concrete structures using techniques that were lost for over 1,000 years after their civilization fell. The ancient Greeks built the Antikythera mechanism, a sophisticated astronomical calculator, using knowledge that vanished until we reinvented similar devices much later. And those were entire civilizations with millions of people. We're asking a few hundred or few thousand people to preserve vastly more complex technical knowledge for far longer, with no possibility of external help if something is forgotten. Let's discuss celestial mechanics and the gravitational challenges that make interstellar travel even more difficult than it appears. Space isn't just empty void, it's curved by mass, filled with gravitational fields that pull and tug on everything moving through it. To escape Earth's gravity, you need to reach about 7 miles per second, what we call escape velocity. But Earth's gravity is relatively weak. To escape the Sun's gravitational influence from Earth's orbit requires even more energy. And the galaxy itself has a gravitational field that influences everything within it. When you're traveling between stars, you're not moving through flat, empty space. You're climbing out of one gravitational well, your departure star, and falling into another, your destination star. This requires careful energy management. You need enough velocity to escape your starting point, but not so much that you can't slow down at your destination. And remember, every bit of fuel you carry to slow down at the end adds mass that you need to accelerate at the beginning. It's another vicious cycle that makes the energy requirements even more impossible. There's also the three-body problem, one of the most famous, unsolved problems in classical physics. We can precisely predict the orbit of two objects around each other, like Earth and the Moon, but add a third object, and the mathematics becomes chaotic. We can't solve it exactly, we can only approximate. Now imagine navigating a spacecraft through a galaxy containing hundreds of billions of stars, each one exerting gravitational influence. The calculations required to plot a precise course over light years become staggeringly complex. Small errors compound over distance and time. What starts as a tiny miscalculation when you depart could result in missing your target by billions of miles after years of travel. Some people point to gravity assists, the technique we use to send probes like Voyager to the outer solar system. You fly close to a planet and use its gravitational field to alter your trajectory and speed, essentially stealing a tiny bit of the planet's orbital energy. It's elegant and efficient, and we've used it to great effect within our solar system. But gravity assists only work when there are massive objects along your route, positioned at the right place at the right time. Between stars, there's nothing. No planets to swing around, no gas giants to borrow speed from. Just emptiness for trillions of miles. The gravity assist technique that works so well for interplanetary travel is useless for interstellar journeys. Here's another crushing reality that science fiction usually ignores. You can't steer in space the way ships steer on water or aircraft steer in air. On Earth, steering works because you're pushing against something, water or air. In the vacuum of space, there's nothing to push against. You steer by firing thrusters, ejecting mass in one direction to push yourself in another direction according to Newton's third law. Every course correction requires expending fuel, and fuel is mass, and mass is your enemy when you're trying to reach relativistic speeds. You need to plot your course with incredible precision before you launch, because you'll have extremely limited ability to correct errors during the journey. Let's examine what happens at your destination, assuming you somehow overcome every obstacle we've discussed and actually arrive at another star system. You've traveled for decades or centuries, you're exhausted, your ship is barely functioning, and you've finally reached the planet that looked promising from Earth. Now what? You can't just land. You first need to slow down, which requires roughly the same amount of energy that it took to accelerate in the first place. If you used all your fuel accelerating, you have nothing left to decelerate. You'll shoot past your destination at whatever speed you arrived with, unable to stop. So you need to carry enough fuel or energy for both acceleration and deceleration. That immediately doubles your energy requirements, which we've already established are impossibly high. Some mission designs propose using the destination star's light for deceleration, deploying a massive light sail and letting the star's radiation pressure slow you down. It's theoretically possible, but the distances and timing involved are extraordinarily difficult. You'd need to deploy your sail precisely, orient it correctly, and maintain that orientation for years as you gradually shed velocity. Any error, and you either don't slow down enough shooting past your target, or you slow down too much and end up in an orbit you didn't intend. Assuming you successfully enter orbit around your target world, you now face the challenge of actually landing. You've been in microgravity or low acceleration for the entire journey. Your muscles have atrophied, your bones have lost density, your cardiovascular system has adapted to not fighting gravity. Even if you exercised religiously during the voyage, you're not in condition to immediately function in a gravitational field that might be stronger than Earth's. You'll need time to readapt, time you might not have if your ship's systems are failing or your supplies are depleted, and what's waiting for you on the surface. You've based your entire mission on observations made from Earth, indirect data suggesting this world might be habitable, but you don't know the details. What's the atmospheric composition? Earth's atmosphere is 21% oxygen, 78% nitrogen, with traces of other gases. If your target world has 15% oxygen, is that enough? What if it has 30% oxygen? That's dangerously flammable. Small variations in atmospheric chemistry could mean the difference between a new home and a toxic nightmare. What about the biosphere? If the planet has life, and that's presumably why you chose it, that life evolved completely independently of Earth life. The biochemistry could be radically different. Proteins might be built from different amino acids. DNA, if it exists at all, might use different nucleotides. The metabolic processes might produce compounds that are lethal to Earth life. You might not be able to eat anything native to this world. It might not be able to eat you either, which sounds good, until you realize that means your body won't decompose properly. The microbial ecosystem that breaks down organic matter on Earth might have no analog here. Or worse, the local life might be able to interact with you in harmful ways. Imagine bacteria or viruses that don't care about the differences in biochemistry and can still infect you, but your immune system has no evolutionary experience fighting them. You'd be as vulnerable as Native Americans were to European diseases, except there's no possibility of developing immunity because you're the only humans in this entire star system. One colonist contracts an alien infection, and it could wipe out your entire population before you even understand what's happening. Then there's planetary conditions we take for granted on Earth. Our planet has a magnetic field that protects us from solar radiation. Does your destination world have one? If not, you're back to the radiation problem, except now you're stuck on a planet with no magnetosphere, constantly bombarded by the star's particle emissions. You'd need to live underground or in heavily shielded structures, surrendering any hope of living naturally on the surface. What about plate tectonics? Earth's active geology recycles nutrients, regulates climate through volcanic outgassing, and creates diverse terrain. A geologically dead world might be stable with no earthquakes, but it would also lack many of the processes that make Earth habitable. Conversely, a world that's too geologically active could have constant volcanic eruptions, frequent massive earthquakes, or a shifting surface that makes permanent settlement nearly impossible. Day length is another factor we rarely consider. Earth's 24-hour day is so ingrained in our biology that changing it might be physically harmful. Our circadian rhythms, our sleep cycles, our hormonal patterns are all tuned to roughly 24 hours. What if your destination world rotates faster with a 15-hour day? Or slower with a 40-hour day? Can humans adapt to that? Some research suggests that chronic circadian disruption leads to serious health problems. You might be living on a habitable planet, that slowly damages your health simply because the day-night cycle doesn't match your evolutionary programming. Gravity is perhaps the most critical factor. If your destination has significantly higher gravity than Earth, even 30 or 40% higher, it would make every physical task exhausting. Your heart would struggle to pump blood. Your joints would experience constant stress. Pregnancy and childhood development might be affected in ways we can't predict. Lower gravity has its own problems. If it's too low, you'd experience the same bone and muscle loss that astronauts face in microgravity. There might be a relatively narrow range of gravitational strength that humans can tolerate long-term, and most exoplanets won't fall within that range. Let's talk about something rarely discussed in optimistic visions of interstellar colonization: the psychological impact of realizing you're utterly alone. When the first colonists of the Americas arrived, they were far from Europe, but they knew Europe still existed. Ships could sail back and forth, news could travel. Help could theoretically arrive, but an interstellar colony is different. You're so far from Earth that light, the fastest thing in the universe, takes years to make the journey. Earth might as well not exist. Everyone you left behind is dead. The civilization that sent you has probably changed beyond recognition, and you can never go back. Even if you wanted to, even if you built another ship and somehow found the energy to launch it, you'd be returning to an Earth that's centuries or millennia ahead of when you left. You're not just isolated in space, you're isolated in time. The loneliness of that realization, the finality of it, could break people psychologically. Depression, anxiety, and existential despair might be inevitable when you truly comprehend that you're not just far from home, but effectively outside of human history, a branch cut off from the tree with no possibility of reconnection. Your colony, if it survives, will be the only humans in that entire region of space. If you fail, if disease or disaster or social collapse wipes you out, nobody will know. Earth might still be sending signals, messages of encouragement or information, not knowing that they're arriving at a dead world, that the recipients have been gone for decades. Those signals will continue indefinitely, monuments to a failed dream, arriving at abandoned settlements where no one remains to receive them. Now let's discuss the uncomfortable mathematics of minimum viable population. How many people do you need to establish a sustainable colony? Geneticists have studied this question extensively in the context of endangered species and isolated human populations. The consensus is that you need a minimum of about 500 to 1,000 genetically diverse individuals to avoid inbreeding depression over multiple generations. Below that number, genetic problems accumulate, leading to increased rates of genetic disorders, reduced fertility, and eventual extinction through genetic collapse. But here's the devastating part. Remember when we discussed the impossibility of sending even small masses to other stars? Now we're talking about sending 500 to 1,000 people, each weighing roughly 100 to 200 pounds, plus all their supplies, equipment, habitat modules, seeds, genetic samples, tools, and everything else needed to establish a civilization on a new world. The total mass would be enormous, easily tens of thousands of tons. Accelerating that much mass to a significant fraction of light speed would require energy measured in significant fractions of our sun's total output. It's not just difficult, it's so far beyond our capabilities that calling it impossible understates the problem. Some proposals suggest sending frozen embryos instead of adult humans, dramatically reducing mass. You'd send genetic material and artificial wombs growing the first generation after arrival, but this introduces a new devastating problem. Who raises these children? Are we proposing that machines raise the first generation of colonists? Can AI provide the emotional nurturing, the cultural transmission, the human connection that children need to develop properly? Even if technically possible, The ethical implications are staggering. You'd be creating humans who've never known human contact, raised by machines on an alien world, expected to build a civilization from nothing with no adults to guide them. Let's examine the political and social devastation that interstellar travel would create. Imagine the global debate that would precede any serious interstellar mission. We're talking about investing resources equivalent to multiple years of total global economic output for a project that won't show returns for decades or centuries. Which nations contribute? Who decides where the mission goes? Who gets to send colonists if it's a crewed mission? The political negotiations would be nightmarish, and that's assuming nations could cooperate at all. History suggests they couldn't. Humanity has never successfully coordinated on projects of this scale, even when the benefits were clear and immediate. Climate change threatens our entire civilization, yet we struggle to agree on actions to address it. International cooperation exists, but it's fragile and often superficial. Now imagine trying to get every major nation to commit to a project that will consume vast resources for generations, with no tangible benefit to anyone currently alive. The political will simply doesn't exist, and there's no reason to think it ever will. Even within a single nation or coalition, the domestic politics would be brutal. How do you justify spending trillions on space exploration when people are hungry, when infrastructure is crumbling, when healthcare systems are underfunded, when education needs improvement? The moral argument against interstellar missions is compelling. Those resources could transform life on Earth for billions of people, right? Now today, choosing to send a handful of explorers to another star instead means consciously deciding that speculative future benefits outweigh certain present needs. It's a choice that's nearly impossible to defend ethically. And who gets to go? If you're sending colonists, you're effectively choosing which humans get to potentially survive if Earth faces catastrophe and which don't. The selection criteria would be contentious at best, explosive at worst. Do you select based on skills needed for the colony? That makes practical sense, but creates an elite group chosen for their abilities. Do you include diversity to represent all of humanity? That's noble, but might not align with practical needs. Do you hold a lottery? That's fair, but means critical skills might be left behind. There's no selection method that won't create massive resentment and accusations of injustice. Let's talk about the legal framework, or rather, the complete absence of one. Current space law, primarily the Outer Space Treaty of 1967, establishes that no nation can claim sovereignty over celestial bodies. Space is the common heritage of humankind. But that treaty was written when interstellar travel was pure fantasy. What happens when a colony actually exists on a planet light years away? Who has jurisdiction? Can Earth claim authority over people who are effectively outside Earth's light cone, so distant that communication takes years? Can the colony declare independence, and if so, under what legal framework? These aren't abstract questions, they have real implications. If a crime occurs aboard a generation ship 10 light-years from Earth, who investigates? Who prosecutes? What laws apply? The laws of the nation that launched the ship. But that nation might not even exist anymore after multiple generations. The laws the colonists create for themselves. But what gives them legitimacy? There's no existing legal or political philosophy that adequately addresses governance across interstellar distances and timescales. We'd be creating human communities with no clear legal status, no established rights, and no mechanisms for justice or governance beyond what they create themselves in isolation. Now let's discuss something that sounds like science fiction, but represents a real concern for any civilization attempting interstellar travel: the possibility of technological obsolescence during the journey. Imagine launching an interstellar mission using the best technology available in 2050. The journey will take 200 years, but technology on Earth doesn't stop advancing just because you launched a ship. By 2100, just 50 years after launch, Earth's technology has advanced significantly. They can now build ships that travel twice as fast using half the energy. Do they launch a second mission that will overtake the first? That seems cruel to the first crew, who are now obsolete before they're even halfway to their destination. But not launching a better mission when you can seems wasteful. This creates a devastating paradox. The best time to launch an interstellar mission is always in the future, when technology will be better. But if you keep waiting for better technology, you never launch at all. And if you do launch, you face the real possibility that you'll be overtaken by later missions using superior technology, arriving at a destination where people who left Earth centuries after you have already been waiting for decades. This isn't just theoretical. It's called the incessant obsolescence postulate, and it's a serious problem for any civilization attempting long-duration space missions. The psychological impact on the crew would be devastating. You've sacrificed everything, spent decades or your entire life traveling to a new world, and you arrive to find that people using technology developed after you left have already established themselves. You're the primitive ancestors, the slow boat, the obsolete relic of an earlier era. Let's examine the energy sources available for interstellar travel in more detail, because this is where the physics becomes truly unforgiving. We've discussed that chemical rockets are far too slow. Nuclear fission provides more energy, but still nowhere near enough for relativistic speeds. Nuclear fusion, if we ever master it, would be better but still insufficient for the energy demands of accelerating significant mass to a meaningful fraction of light speed. We mentioned antimatter, which has theoretical potential, but production problems that are essentially insurmountable. What else is there? Some physicists have proposed using black holes as engines. A sufficiently small black hole, perhaps the mass of a mountain, would emit Hawking radiation that could theoretically be harnessed for propulsion. The problem? We don't know how to create small black holes. We don't know how to capture them if they exist naturally, and we certainly don't know how to safely contain and utilize one as a power source. The engineering challenges are so far beyond our current capabilities that discussing them feels like medieval scholars speculating about nuclear reactors. Others have suggested harvesting energy directly from stars. Build enormous solar collectors, perhaps Dyson swarms of satellites, that capture a significant fraction of a star's output and direct that energy toward accelerating your spacecraft. It's an idea that fits within known physics, unlike some other speculative propulsion methods. But the scale is incomprehensible. We're talking about constructing infrastructure in space that dwarfs anything humanity has ever built. The mass required would be measured in billions or trillions of tons. The construction time would span centuries. And all of this would be necessary just to launch a single interstellar mission. Even if we could somehow build such infrastructure, we face the fundamental problem that stars produce enormous amounts of energy, but most of it radiates into space unused. The Sun produces about 3.8 times 10 to the 26th watts of power. That's a number so large it's meaningless to human intuition, but it's spread across all directions. Earth intercepts less than 1/1000th of the Sun's total output. To harness a meaningful fraction of that energy, you'd need to surround the Sun with collectors, and the engineering challenges of that are indistinguishable from magic, given our current technology. Here's another devastating reality: the rocket equation. This is fundamental physics discovered by Konstantin Tsiolkovsky in 1897, and it's been the bane of space travel ever since. The equation tells us that the change in velocity your rocket can achieve depends on the exhaust velocity of your propellant and the ratio of your rocket's initial mass to its final mass. To go faster, you either need higher exhaust velocity or a higher mass ratio, meaning more fuel relative to payload. But here's the cruel part: the relationship is logarithmic. To double your speed, you need exponentially more fuel. To reach relativistic speeds, even with theoretical engines producing exhaust at significant fractions of light speed, you'd need fuel-to-payload ratios that are astronomically high. Some calculations suggest mass ratios of millions to 1 or higher. That means for every pound of payload, you need millions of pounds of fuel. It's physically impossible to build a rocket that's mostly fuel to that degree. The fuel tanks themselves would have more mass than you can carry. Some propulsion concepts try to cheat the rocket equation by not carrying fuel at all. Light sails accelerated by lasers from the origin point are one example we discussed earlier. Another is the Bussard ramjet, a theoretical engine that would scoop up hydrogen from the interstellar medium and use it as fuel. You'd accelerate it through magnetic fields, fuse it in a fusion reactor, and exhaust it for propulsion. It's elegant because your fuel is the universe itself. You never run out. But the devastating reality is that the Bussard ramjet probably doesn't work. The density of hydrogen in interstellar space is so low that you'd need a scoop hundreds or thousands of miles in diameter to collect enough for meaningful thrust. The structure needed to create and maintain such an enormous magnetic field would have massive amounts of mass itself, and that mass needs to be accelerated too. Detailed calculations done in the late 20th and early 21st centuries suggest that the drag from collecting the hydrogen might exceed the thrust you gain from burning it. You'd actually slow down. The elegant solution doesn't solve anything. Let's discuss wormholes and warp drives because inevitably someone will ask, what about the exotic solutions? What about the science fiction concepts that physicists say might be theoretically possible? The truth is devastating in a different way because these ideas dangle hope in front of us while remaining forever out of reach. Wormholes, shortcuts through space-time connecting distant points, are permitted by Einstein's equations under certain conditions. The problem is those conditions require something called exotic matter, matter with negative mass energy. Does exotic matter exist? We don't know. We've never observed it. We have no idea how to create it. Even if it exists, we don't know how to manipulate it. And even if we could manipulate it, the amounts required to hold open a wormhole large enough for a spacecraft to pass through would be enormous, possibly requiring the mass energy of multiple stars. We're not talking about technology that's 50 years away or 100 years away. We're talking about technology that might be impossible because it requires forms of matter that might not exist in our universe. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, is another tantalizing concept. The idea is that you don't move through space at all. Instead, you compress space in front of your ship and expand it behind you, creating a bubble of normal space that surfs on a wave of distorted space-time. The ship itself isn't moving relative to the space immediately around it, so you don't violate the light speed limit. In theory, the bubble could move faster than light. It's brilliant, and the mathematics work within general relativity, but the devastating problems are similar to wormholes. You need exotic matter with negative energy density. The amounts required in early calculations were absurd, roughly equivalent to the mass energy of the entire visible universe converted to this exotic form. Later refinements reduced the requirements, but even the most optimistic calculations require energy equivalent to the mass of Jupiter or larger. And that's assuming exotic matter exists and can be controlled, which we don't know. There's another problem with warp drives that's even more fundamental. Research published in the early 21st century suggests that the interior of a warp bubble would be causally disconnected from its exterior. That means the people inside the bubble couldn't control it. They couldn't steer. They couldn't turn it on or off. They'd be helplessly carried along by whatever external mechanism created the bubble. This makes the warp drive useless as a practical transportation method, even if we somehow solve the energy and exotic matter problems. Some physicists argue that quantum effects might make wormholes and warp drives genuinely impossible, not just impractical. Stephen Hawking proposed what he called the chronology protection conjecture. Essentially, the idea that the laws of physics prevent time travel and other causality-violating phenomena. Wormholes and warp drives could potentially enable time travel under certain configurations, which might mean the universe simply doesn't allow them to exist. We're not just facing engineering challenges, we might be facing fundamental prohibitions written into the structure of reality itself. Let's talk about cosmic hazards that would threaten any interstellar journey. Space isn't just empty void, it's filled with phenomena that range from inconvenient to instantly lethal. We've discussed micrometeorites and cosmic radiation, but there's more. Interstellar clouds, regions where gas and dust are denser than average, would be like flying through a sandblaster at relativistic speeds. You can't see them coming in time to avoid them. Even if you could, changing course requires energy you might not have. Rogue planets, worlds ejected from their star systems, drift through the galaxy in darkness. We've detected some, but there could be billions or trillions of them. They're effectively invisible unless they happen to pass in front of something brighter. A collision with a rogue planet would be catastrophic, but even a near miss could gravitationally disrupt your trajectory, throwing your carefully calculated course completely off. And you wouldn't know it happened until you were far past your intended destination, decades or centuries off course, with no way to correct. Supernovas represent another existential threat. When a massive star explodes, it releases more energy in a few weeks than our Sun will produce in its entire 10 billion-year lifetime. The explosion sends out a shell of matter traveling at a significant fraction of light speed and a burst of radiation across the entire electromagnetic spectrum. If a star along your route or near your destination goes supernova during your journey, the radiation could sterilize your ship. You'd have no warning, no way to shield yourself adequately, and no possibility of survival. The probability of a nearby supernova during a journey lasting centuries is actually not trivial. Supernovas occur in our galaxy a few times per century on average. Most are far away and pose no threat, but space is three-dimensional, and you're traveling through a volume of it over long timescales. The risk accumulates. It's another dice roll, another way the universe can destroy your mission randomly and without warning. Gamma-ray bursts are even more terrifying. These are the most energetic events in the universe, probably caused by colliding neutron stars or certain types of supernovas. They release jets of gamma radiation so intense that a burst occurring thousands of light-years away could cause mass extinctions on Earth if one of the jets happened to point toward us. For an interstellar spacecraft, a gamma-ray burst anywhere along your route or near your destination would be absolutely lethal. The radiation would penetrate any shielding practical to carry, killing the crew and destroying electronic systems. And you'd have no warning. Gamma-ray bursts travel at the speed of light. The deadly radiation arrives at the same time as any signal that could warn you. You wouldn't see it coming. One moment everything is fine, the next moment everyone aboard is receiving a lethal radiation dose. There's no protection, no escape, no survival. It's cosmic bad luck. And the timescales involved in interstellar travel mean you're exposed to that possibility for far longer than any humans have ever been before. Let's discuss something we haven't fully addressed yet: the philosophical and existential questions that interstellar travel raises. If the difficulties are truly insurmountable, what does that mean for humanity's long-term future? Our Sun will eventually die. In about 5 billion years, it will expand into a red giant, engulfing the inner planets, including Earth. Long before that, in perhaps 1 billion years, the Sun's increasing luminosity will make Earth uninhabitable. If we can't leave the solar system, we're ultimately doomed to extinction when our star dies. Some argue we could survive in our solar system for billions of years by moving to the outer planets as the Sun expands or building artificial habitats. That's technically true, but it's a finite solution. Eventually, the sun will collapse into a white dwarf and slowly cool over trillions of years. The solar system will become a frozen, dark graveyard. If we're still here, confined to our birth system, we'll freeze in the darkness. Interstellar travel isn't just about exploration or curiosity. It's about whether humanity has any long-term future at all. But if interstellar travel is truly impossible, we need to confront an uncomfortable truth. We might be alone, not because alien civilizations don't exist, but because all civilizations are trapped in their home systems just as we are. The galaxy could be filled with intelligent species, each one confined to their stellar neighborhood by the same insurmountable physics we face. We're all prisoners of the same cosmic constraints, forever separated by distances too vast to bridge. This is sometimes called the Great Silent Solution to the Fermi Paradox. Enrico Fermi famously asked, "Where is everybody?" Given the age and size of the galaxy, we should see evidence of alien civilizations if they exist. The fact that we don't is puzzling. One explanation is that interstellar travel and communication are so difficult that even advanced civilizations rarely attempt them, and successful attempts are even rarer. The galaxy could be teeming with life, but everyone's stuck at home, shouting into a void too large for sound to cross. There's a darker interpretation of the Great Filter hypothesis that we need to discuss. The Great Filter concept, proposed by economist Robin Hanson, suggests there's some extremely difficult step in the evolution of intelligent spacefaring life. This filter is so difficult that it prevents most potential civilizations from ever spreading through the galaxy. The terrifying question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, that's actually good news. It means the hard part was evolving intelligent life in the first place, and we've already passed it. The path ahead, while challenging, is open. But if the filter is ahead of us, if the truly insurmountable obstacle lies between where we are now and becoming a spacefaring civilization, then we're in trouble. It would mean that something destroys or stops virtually all civilizations at roughly our stage of development. And the fact that we see no evidence of alien civilization suggests that very, very few make it through whatever that filter is. Could interstellar travel itself be the great filter? Could the physics of the universe be so unforgiving that no species ever successfully establishes interstellar colonies, no matter how advanced they become? It's a sobering thought. We've spent this entire exploration documenting why interstellar travel is so difficult, why every approach runs into fundamental physical barriers that might be insurmountable. If we're right, if these barriers truly can't be overcome, then we've identified the great filter, and it's ahead of us, and it stops everyone. This connects to another devastating concept: cosmic loneliness. Even if we're not alone in the universe, even if the galaxy is full of civilizations, the distances and difficulties might mean we'll never meet any of them. We might detect radio signals, faint whispers from across the void, proving someone else exists. But the conversation would be painfully slow. A transmission from a civilization 1,000 light-years away takes 1,000 years to reach us. Our reply takes another 1,000 years to reach them. A simple exchange takes 2 millennia. Multiple generations would live and die between question and answer, and that assumes the other civilization still exists when your reply arrives. Civilizations rise and fall. On Earth, the longest-lasting continuous civilizations have persisted for perhaps 4,000 years before transforming into something different. A conversation across 1,000 light-years requires civilization stability measured in millennia. One side could easily collapse, die out, or transform beyond recognition while the other side's message is still in transit. You might be answering a question posed by a civilization that's now extinct, your reply arriving at abandoned ruins where no one remains to hear it. The psychological impact of this cosmic isolation extends beyond individual missions. It affects our entire species' self-image and purpose. Humanity has always been explorers, We've spread across every continent, adapted to every environment, pushed into every frontier. It's core to our identity as a species. But interstellar space might be the first frontier that pushes back harder than we can push forward. For the first time in our history, we might be facing a barrier that determination, ingenuity, and courage can't overcome. What does that do to our collective psyche when we realize we're not the unstoppable explorers we thought we were, but prisoners of physics confined to a single star system? Let's examine one more proposed solution. Von Neumann probes, self-replicating machines that could explore the galaxy on our behalf. The idea is elegant. You send out a probe to another star system. When it arrives, it uses local resources to build copies of itself, which then travel to other star systems and repeat the process. Exponential growth means that even without faster-than-light travel, these probes could theoretically explore the entire galaxy in just a few million years, a blink of an eye on cosmic timescales. It sounds promising until you examine the details. First, these probes would need to be extraordinarily sophisticated, capable of landing on planets or asteroids, extracting and refining raw materials, manufacturing complex components, and assembling perfect copies of themselves, all autonomously without human guidance. We can barely build robots that can navigate unpredictable terrain on Earth with constant oversight. Building machines that can operate independently for centuries and then manufacture copies of themselves in alien environments is technology so far beyond our current capabilities that it's not meaningfully different from magic. Second, there's the control problem. Once you launch self-replicating machines, how do you control them? How do you prevent mutations, errors that creep into the replication process over generations? On Earth, biological evolution is driven by replication errors. The same would happen with self-replicating machines. After thousands or millions of generations, probes replicating in distant star systems might bear little resemblance to the originals. They could evolve unpredictable behaviors, they could malfunction, they could become dangerous. Some theorists worry about the grey goo scenario, where self-replicating machines malfunction and consume all available matter to make more copies of themselves. It's probably unrealistic as stated, but it points to a real concern. Self-replicating technology is inherently dangerous. Once released, it can't be recalled. Errors compound. Control is lost. You're essentially releasing an artificial evolution process into the galaxy with no way to predict or control the outcome. The probes that return, if any do, might be nothing like what you sent out. And even if von Neumann probes work perfectly, what have you accomplished? You've explored the galaxy by proxy, you've gathered data. That's valuable, certainly, but it's not the same as human presence, human settlement, human experience. Sending machines to explore while we remain trapped at home is like reading travel brochures instead of taking vacations. It's information without experience, knowledge without participation. If the goal is to make humanity an interstellar species, von Neumann probes don't achieve that. They just confirm that we can send our robots where we ourselves can't go. There's also the timeline problem with any robotic exploration. Even von Neumann probes traveling at reasonable fractions of light speed would take millions of years to thoroughly explore the galaxy. Humanity has existed as a species for only about 300,000 years. Civilization has existed for roughly 10,000 years. Modern technological civilization is less than 300 years old. Can we reasonably expect our civilization to persist for millions of years, maintaining continuity and purpose long enough to receive data from probes that won't return for longer than our entire history as a species? It's asking for a level of civilizational stability that no evidence suggests is possible. Let's talk about the economic opportunity cost in more concrete terms. Imagine the global community decides to fund an interstellar mission. Conservative estimates put the cost at multiple trillions of dollars, possibly tens of trillions. That same money invested in Earth-based problems could transform human civilization. It could end hunger, provide clean water globally, cure diseases, reverse environmental damage, build sustainable energy infrastructure, lift billions out of poverty. The ethical calculation is brutal. Do you spend resources that could save millions of lives today on a project that might benefit a tiny handful of people decades or centuries from now, if it works at all? The answer most ethicists would give is clear: you don't. The moral obligation to help people suffering right now outweighs speculative future benefits. This creates a devastating bind. The only time it becomes ethical to pursue interstellar travel is when all our pressing problems are solved, when everyone has enough, when suffering has been eliminated. But if we reach that utopian state, would we still feel the drive to leave? If Earth is paradise, why risk everything to go elsewhere? The motivation for interstellar travel is strongest when conditions are worst, but that's precisely when it's least justifiable to pursue it. Let's examine the timeline problem from another angle. Suppose we solve every technical challenge we've discussed. We develop fusion power or antimatter production or some other revolutionary energy source. We build the infrastructure to construct massive spacecraft. We recruit volunteers willing to spend their lives traveling between stars. We launch a mission to Alpha Centauri using the best technology available in, say, 2100. The journey takes 80 years. But technology keeps advancing on Earth. By 2120, just 20 years after the first mission launched, new discoveries allow ships to make the journey in 40 years. Do you launch a second mission? If you do, it arrives 40 years before the first mission, meaning the backup crew arrives first. The original pioneers become irrelevant, their sacrifice meaningless because they're traveling on an obsolete ship that newer technology has already surpassed. How do you maintain morale among the first crew when they receive messages informing them that later missions have overtaken them and reached the destination already? Now extend this logic. Maybe by 2140, ships can make the trip in 20 years. By 2160, 10 years. At what point is the technology good enough that you can commit to a mission without worrying about being overtaken? The answer might be never. There might always be reason to wait just a little longer for better technology. This creates temporal paralysis, where the rational choice is always to delay, which means nothing ever launches. There's a related problem with generational continuity of purpose. Interstellar missions would take decades to plan and prepare, and centuries to complete. The people who plan the mission won't live to see it launch. The people who build it won't see it depart. The people who launch it won't see it arrive. How do you maintain focus and commitment across multiple generations for a project with such delayed gratification? Human institutions struggle to maintain purpose over just a few decades. Corporations rarely last a century. Governments transform every few generations. Expecting multi-century project continuity requires social stability we've never demonstrated. Consider the Apollo program, one of humanity's greatest achievements. From Kennedy's speech committing America to the moon to Armstrong's first steps was just 8 years, relatively quick, visible results within a single generation, and even that program faced constant political pressure, budget cuts, and eventual cancellation before all planned missions were completed. The political will existed because results came quickly enough that the same people who authorized the spending could see the benefits. Interstellar missions offer no such immediacy. Everyone who approves the spending will be dead long before success or failure is known. Let's discuss the information problem. Even if we successfully establish an interstellar colony, what have we actually accomplished? The colony is effectively lost to Earth, separated by distance so vast that meaningful interaction is impossible. Scientific discoveries made by the colony will take years to transmit back to Earth, and by the time they arrive, they might be obsolete. Earth's science continues advancing too. The information moving at light speed in both directions creates two divergent knowledge bases that can't effectively share or build on each other's work. Cultural evolution creates similar divergence. The colony's culture will evolve independently, shaped by its unique environment and challenges. After a few generations, colonists might have little in common with Earth beyond biological ancestry. They'd be a separate branch of humanity, isolated and different. Is that the goal? To fragment our species into disconnected pockets scattered across the galaxy, each evolving in its own direction? It's not expansion in any meaningful sense, it's fragmentation, the breaking apart of human civilization into pieces that can never rejoin. Some optimists argue that this fragmentation is actually beneficial. Multiple independent human colonies means our species isn't vulnerable to a single catastrophic event. If Earth is destroyed, humanity survives elsewhere. It's the backup argument, the idea that interstellar colonization is existential insurance. But the argument collapses under examination. The resources required for interstellar colonization are so enormous that if we have them available, we could instead build robust habitats in our own solar system. Orbital colonies, underground bases on Mars, floating cities in Venus's atmosphere, habitats in the asteroid belt, all would be orders of magnitude cheaper and easier than interstellar missions. A disaster severe enough to threaten all life on Earth would also threaten these solar system habitats, true, but they're close enough for evacuation and mutual support. An interstellar colony provides no additional safety because it's too distant to help or be helped. If Earth is destroyed, the colony continues existing in isolation, but Earth people don't survive. They're gone. The colony is not an extension of Earth civilization, it's a separate entity. The backup argument only works if you define humanity surviving as merely having biological humans somewhere in the universe, even if they're completely disconnected from us and our culture. Now let's confront perhaps the most devastating realization of all. The universe might be fundamentally structured to prevent interstellar civilizations. The physics of relativity, the vast distances between stars, the energy requirements for travel, the dangers of radiation and cosmic hazards, all of these aren't just challenges, they're features of how our universe operates. The universe is built in a way that keeps civilizations isolated. Why would the universe be structured this way? We don't know. Maybe it's just how physics works with no deeper reason, or maybe there are anthropic considerations. Perhaps in universes where interstellar travel is easy, something else goes wrong that prevents the evolution of intelligent life. Maybe the difficulty of interstellar travel is correlated with other physical constants that make life possible in the first place. We exist in a universe where interstellar travel is nearly impossible precisely because that's the only type of universe where beings like us can evolve to ask the question. This leads to an uncomfortable philosophical conclusion. Our dreams of spreading through the galaxy might be fundamentally misaligned with reality. We evolved on a planet, and planets exist in star systems, and star systems are separated by distances that are hostile to travel. We evolved to explore continents and oceans, but the skills and drives that made us successful on Earth don't translate to the cosmic scale. We're like fish that evolved in a pond, dreaming of exploring the ocean, but the land between our pond and the ocean is impassable. The dream isn't wrong, but the reality doesn't accommodate it. Some argue that future technology will solve these problems, that we can't imagine what might be possible in 1,000 or 10,000 years. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. Maybe future humans will have capabilities we can't conceive. But this argument is just hope disguised as reasoning. It's true that we can't predict all future discoveries, but we can identify fundamental physical limits. We know, for instance, that nothing with mass can travel faster than light. That's not a technological limitation, it's a structural feature of space-time itself. No amount of advancement changes it. Similarly, the energy requirements for accelerating mass to relativistic speeds aren't engineering problems, they're physics problems. The energy is quantifiable using equations we understand. Future technology might find more efficient ways to generate and apply that energy, but it can't change the fundamental calculation. If the energy required exceeds what any realistic civilization can produce, then the barrier isn't technological, it's absolute. Hoping that future technology will somehow work around the laws of physics isn't rational planning, it's wishful thinking. Let me be clear about what I'm not saying. I'm not claiming that interstellar travel is literally impossible in every conceivable scenario. Extremely slow generation ships traveling for thousands of years might technically work, assuming we solve the life support, social stability, and longevity challenges. Tiny light sail probes pushed by enormous laser arrays might reach nearby stars, assuming we build the infrastructure and perfect the targeting. What I'm saying is that the practical, realistic challenges are so severe that interstellar travel is effectively impossible for any civilization remotely like ours, operating under physics as we understand it. And here's the final devastation. We might never know for certain. If we're right, if interstellar travel is truly insurmountable, we won't discover that through failure because we'll never attempt missions ambitious enough to fail. The projects would be too expensive, too long-term, too risky. We'll simply never try. Future generations might look back and wonder if we could have done it if we'd really committed. But they won't know, and neither will we, because the attempt itself is beyond our civilization's capacity to organize and sustain. This leaves us in a strange position. We live in a universe vast beyond comprehension, filled with billions of galaxies, each containing billions of stars, many hosting planets, some presumably harboring life. We can see it all through our telescopes. We can study it, measure it, understand it, but we probably can't touch it. We're observers, trapped in our small corner of space, able to look but not reach, condemned to wonder about worlds we'll never visit and civilizations we'll never meet. The cruel irony is that our intelligence, the trait that allows us to dream of the stars, also allows us to calculate exactly why we'll never reach them. We're smart enough to understand the prison we're in, but not powerful enough to escape it. We can imagine interstellar civilization, write stories about it, create detailed visions of humanity spreading through the galaxy. But imagination isn't enough. Physics doesn't care about our dreams. So what do we do with this knowledge? Some would say it's depressing, that recognizing the limits of what's possible crushes human spirit. I disagree. There's freedom in accepting reality. If we acknowledge that interstellar travel is beyond our reach, we can stop fantasizing about escape and start taking seriously our responsibility to the one planet we'll ever call home. Earth isn't a launching pad for our journey to the stars. It's our permanent home, the only home we'll ever have. That makes it infinitely more precious. Maybe the lesson is that we need to shift our perspective. Instead of looking outward and dreaming of conquest, maybe we should look inward and dream of sustainability, of building a civilization that can last not just centuries, but millions of years right here. We have one solar system, 8 planets, dozens of moons, countless asteroids. That's our domain, and it's vast enough to occupy humanity for thousands of generations if we're wise about how we use it. The stars will remain out there, beautiful and distant, inspiring wonder but not conquest. We'll study them, learn from them, perhaps detect signals from civilizations as trapped as we are, but we won't walk among them. And maybe that's okay. Maybe the universe is trying to teach us something by making interstellar travel so difficult. Maybe the lesson is that home matters, that the place you're from is the place you belong, and that dreams of escape are less valuable than commitment to making your home the best it can be. Thank you for staying with me through this exploration. I know it's been sobering, perhaps even depressing, but I believe understanding the truth, even when it's uncomfortable, is better than comfortable delusions. We are a species trapped by physics, but we're also a species capable of accepting that truth and finding meaning despite it. The stars are beautiful from here. And here is where we'll stay. If you enjoyed this video, I am sure you will love this other one at the left side of the screen. How long would it actually take to reach Andromeda Galaxy? In this video, we will explore the Hubble telescope observations revealing Andromeda's trillion stars and violent merger history, the approaching collision in 4 billion years forming Milkomeda, generation ships requiring closed-loop ecosystems, and much more. See you there.